In this particular lecture, we will talk about the thermodynamic stability as well as the different stability constants, right? So for that, please consider this equilibrium reaction here in which the copper ions are reacting with 4 ammonia as the ligands, resulting in the formation of this type of tetramine copper 2 ion complex, right? Now, whenever some reaction is present at equilibrium, there is a possibility that the reaction may either shift towards this direction, means towards the right, or the formation of this complex here. And the second possibility is, of course, that it may shift in this direction here, resulting in the formation of these ions, or let us say the dissociation of this complex here, right? So obviously, if this complex here is more stable in nature, this equilibrium here will be definitely shifting towards this direction or the right direction here, right? So this means that the Ks here, I mean the equilibrium constant, is actually related with the stability of this complex here. So we can say here that if the complex here is more stable, let me write here, it is more thermodynamically stable, in that case, obviously the value of the Ks, means the equilibrium constant, will be quite high, and the equilibrium will tend to shift towards the right hand side, resulting in the formation of this complex here, right? So now we can say that the thermodynamic stability of a complex actually is what it is the measure of the extent of the formation of a complex at equilibrium, right? This means, once again, let me tell you that whenever some reaction is there at equilibrium and the ions are combining, resulting in the formation of some complex which is present on the right hand side, so there are chances that the reaction may go towards either of the side. But if the complex is more thermodynamically stable, obviously the reaction will be going towards the formation of that complex and not towards those individual ions from which it is being formed, right? So in this case here, the copper ions are what they are acting as the metal ions, of course, and the ligand is what you can see here. This is the ligand here. They donate electrons, so it can act as a Lewis base, right? On the other hand, because the metal ions are accepting electrons, so we can call them as a Lewis type of acids, such that we can assume that whatever reaction is occurring here, it is nothing but an interaction of the Lewis acids and the Lewis bases, right? And obviously, if the Lewis base, I mean this ligand here is a strong ligand, let us say is a strong Lewis base, the interaction with this Lewis acid of this Lewis base will be quite stronger, such that it will result in the formation of some complex that will be more thermodynamically stable, and that will be formed very easily, right? So if the ligands are strong, obviously their interactions with the metal ion will be more stronger, and that will result in the formation of a more stable, I mean more thermodynamically stable product that will be formed very easily, right? So once again, the thermodynamic stability is nothing. It is actually the extent to which any complex will be formed whenever the reaction is present in equilibrium, something like this here, right? And after that, of course, I have told you that the Ks here, I mean the equilibrium constant, it is directly related to this thermodynamic stability of the complex. And we can say that higher the value of this Ks here, I mean the equilibrium constant, which we can find by this formula here, means Ks of course will be equal to what? The concentration. This is the concentration of the product molecules, which you can see here. This is the product here, that is the tetramine copper 2 ion, divided by the concentrations of the ions from which it is formed, I mean the concentration of the Cu2 positive ions, which you can see here, as well as the concentration of the ammonia ions, which you can see here. And even because 4 moles of ammonia are being present here, so obviously this concentration term will be raised to the power equal to the number of moles here, which is equal to 4 in this case, right? So this will be the Ks here, that is the equilibrium constant. And we can say that larger the value of this Ks, I mean the equilibrium constant, which you can see here, greater will be the thermodynamic stability of that particular complex formed because of that equilibrium type of reaction, right? So it is that easy to understand that if there is some reaction in equilibrium and if the value of the Ks is quite higher, the complex formed on the right hand side will be having a larger thermodynamic stability and it will be formed very easily, right? So now let's move on to the next slide. So here you can see that the larger Ks values implies the first thing is that the thermodynamic stability will be high. It is that same thing. And moreover, I have also discussed that the equilibrium will shift towards the right direction. Yes, okay. So if the value of Ks is high, you can see here the equilibrium will be shifting towards this right direction here, on which our complex ion is being present from the ions, means the copper and the ammonia, from which it is formed here, right? So this will be having high thermodynamic stability and it will be more stable, of course, right? And after that, here are two examples. The first one is that of the tetramine copper complex and the second one is of the tetracyano copper complex, right? And once again, in this case, obviously the Ks will be what here? It will be the concentration of the product molecules. I mean this here divided by the product of the concentrations of the reactant molecules, means the concentration of copper as well as the ammonia ions, right? And you can see here the value of Ks for this particular reaction is what? It is 4.5 10 raised to the power 21, of course a very high value. And in this case, the equilibrium constant or the value of Ks once again will be what? It will be the concentration of the product molecules, which is this here, divided by the product of, I mean multiply here the concentrations of the reactant molecules. The first one is this Cu2 positive ions and the second one is the cyanide ions, of course. And moreover, you can see here that we have raised this term to the power 4 because 4 is what? It is the number of moles here, right? And even in this case, the value of Ks is quite high. It is 2 into 10 raised to the power 27. So if we want to compare these two values here, we can say that this value here is relatively high. This means what? That whatever complex is present here on the right hand side, it will be thermodynamically more stable, right? It will be formed very easily, and thus it also indicates that the interactions between the cyanide ion as the ligand as well as the copper as the metal ion will also be very high, right? So you can see here that because of the high Ks value, the CuCN4 2 negative is thermodynamically more stable, as well as the interactions between the copper 2 positive metal ions and the Cn negative ligands are more strong, right? On the other hand, in this case, the interactions will be a little less as compared to this case. And finally, we can say here that the cyanide ion is actually a stronger type of ligand as compared to that of the ammonium ion, right? So because in this case the cyanide ion here is acting as a Lewis base, it is acting as a Lewis acid. So the complex formation actually depends upon the interactions of these cyanide ions with that of the copper 2 positive ions, right? And experimentally it has been proved that this complex here is more thermodynamically stable. So what will happen is that it will be formed very easily, right? And as it is formed very easily, this simply implies that the interactions here are what? These are strong type of interactions, which further implies that cyano is what? It is a stronger type of ligand as compared to that of, let me write here, stronger ligand as compared to that of ammonia, in which the interactions between the metal ion and the ligand will be less strong here, and thus the ammonia will be a relatively less strong type of ligand, right? So this is the another thing which such kind of Ks values or the equilibrium constant values tells us about the constituent ions or the ligands and the metal ions from which the transition metal complex is being formed, that what type of ligands are those, whether they are a type of strong ligands or weak field type of ligands, right? So after that, there is another thing that is known as the dissociation constant, and obviously it will be the reverse of what is known as the equilibrium constant, which we have just discussed, right? So this is our old equilibrium reaction, means copper ions, 4 ammonia ions, resulting in the formation of this tetramine copper complex, and this is the Ks here, which we have just discussed, and this is the value here, that is 4.5 10 raised to the power 21, right? And now just imagine if we are writing this equilibrium reaction, I mean this one here in the reverse direction, means sending the complex ion onto this side and the constituent ions onto this side. What will happen is we will be having a situation something like this, right? So we can say that on one side, means this reaction was what? This reaction was about the formation of the complex. Let me write here. This is regarding the formation of the tetramine copper complex, and the other reaction which we have got here is, I mean, this equilibrium reaction here. This is indicating what? It is indicating actually the dissociation. So let me write here, because it is a dissociation of the complex into its constituent ions. You can see here the complex is dissociating. So it is basically a dissociation of this complex here. Now if we go for the equilibrium constant for such kind of equilibrium reaction, once again we will do what here, that on the numerator side we will be carrying out the product of the concentration of the product molecules. So you can see here, this is the product molecule, here is the concentration, and then the product molecule here is the ammonia. So you can see here, this is the ammonia here, raised to the power 4, because there are present 4 number of moles here, right? Divided by the reactants, of course, and in this case the reactant is what? It is acting as the reactant. So the concentration of the complex ion, because it is like this here, right? It is like this here, right? So now if you see here, if you compare this thing with this thing here, you will see that it is just reverse of this. Okay, so if this was the Ks here, obviously the dissociation constant, I mean K dissociation, will be what? It will be reverse of the Ks, means 1 over Ks, and we know the value of Ks here, which is 4.5 10 raised to the power 21. That will give us a final value of 2.2 multiplied by 10 raised to the power minus 22, and this will be the dissociation constant for this dissociation equilibrium reaction, right? And now the important part here to understand is what? That for such type of equilibrium in which the reaction is towards this direction, and if the value of Ks is high, the equilibrium will tend to move towards this right hand side, suggesting that this complex here is what? It is thermodynamically more stable, right? And in this case here, if the value of the dissociation constant, I mean this value which you can see here, is very low, this means this reaction is not going in this direction. Actually it is not going in this direction, or it is very less towards the right hand side, such that it is actually in this type of direction, that this complex here will tend to remain as it is. Okay, it is not dissociating at all, indicating that it is having a high type of thermodynamic stability, So finally we can say here that for high thermodynamic stability, what is required is a very high value of Ks, and the dissociation constant should be what? It should be having a low value. And it is very clear from the formula even, that because the K dissociation is something equal to 1 over Ks, it is the reciprocal of Ks. So if this thing is quite high, obviously the reciprocal will be what? This will be quite low in the numerical values, right? So for high stability, high thermodynamic stability, the Ks should be higher and the value of K dissociation should be lower, right? So this is all about the thermodynamic stability of the complexes, and now let's talk about the stability constants of these complexes. So let us write a general equilibrium reaction here, in which you can see that we are having one metal and n number of ligands are present, resulting in the formation of this complex ion, that is MlN here, right? Now, in order to synthesize or to form this MlN, we have two different types of approaches. This is the first approach here, in which you can see that there is present, the first step is what it is, one metal ion, one ligand, resulting in the formation of this one metal ligand complex, right? And obviously we can always write down the equilibrium constant here. Let us say it is K1. So K1 here will be equal to what? It will be the concentration of the product molecules, that is ml here, divided by the concentrations of the reactant molecules, which is M as well as L, and you can see here the concentration of M is there multiplied by that of the concentration of the L, right? And in this type of strategy, let me write here, this is strategy 1 here. The second step is what? That once this ML is being formed, what we will do is we will add another or the second ligand here, such that now it will result in the formation of this type of Ml2. And let us say in this case, the equilibrium constant is what? It is denoted by this K2, such that it will be equal to this Ml2 concentration divided by the concentration of the reactants, which now is what? It is this Ml multiplied by L here, right? And likewise, we will be adding one ligand step by step, which you can see here now. This is being taken here in the third step, adding another ligand here, resulting in the formation of Ml3. And in the same way, we can calculate the equilibrium constant here, which will be K3 here, right? Because this is the third step, right? And finally, if we want such kind of Mln complex, obviously we will be adding to Mln minus 1 here, one ligand in this way, such that it will result in the formation of this type of MLN. Because if we want 3 ligands here in the final complex, what we want is we want one ligand here and 2 ligand, which is 3 minus 1. 3 is coming from here, minus 1, which gives us 2 here. In the same way, if we want n ligands, we will be taking here what? We will be taking n minus 1 here, which you can see is present here, right? And plus adding one ligand, it will give us what? It will give us Mln, such that the equilibrium constant for this step here, I mean Kn, will be equal to what? It will be the concentration of the product molecules, which is this here, divided by the concentrations of the reactant molecules, which is this one here, and then the concentration of the L, and you can see here it is in this way, right? So such type of equilibrium constants in which the ligands are added in a stepwise manner, I mean this K1 here, K2 here, then is the K3, and finally the Kn. Such type of equilibrium constants are known as the stepwise stability constant, right? Because the reaction is going stepwise. To one metal ion, first of all, one ligand is added, and then the second ligand, third ligand, and it will go on until we achieve this type of complex here, right? And we do have a strategy 2 here. Let me write here. This is the strategy second. It is this strategy second here, which says that if we want this type of complex ion, means Mln, what we can do is we can simply start from the metal ion and we can simply add all the ligands at once here, right? So that in this case, the equilibrium constant will be what? It will be the concentration of the product molecules divided by that of the reactant molecules, which is concentration of M, which you can see here, multiply by the concentration of the L, the ligand I mean, which you can see here, it is like this, raised to the power the number of moles here, which you can see in this case, these are the number of moles, which is denoted by small n here, right? So how we get to know this thing? Because we know that for one metal, one ligand, for the product formation Ml, the beta 1, I mean this equilibrium constant here will be what? It will be Ml divided by the concentration of M and that of the L. In the same way, if we want to synthesize Ml2 type of complex, and we are following strategy 2 in which we are adding all the ligands at once and not step by step. So for the formation of Ml2, we just have to add what? 2 ligands to the same metal ion, and it will result in the formation of Ml2, and the equilibrium constant In that case, will be what it will be this here, right? And similarly for Ml3, we will be adding all the three ligands at once, resulting in the formation of this type of equilibrium constant. So from all these information here, we will get to know that if we want to synthesize MlN, we will be adding all the N ligands at once, resulting in the formation of this thing, such that the equilibrium constant, which is denoted by beta N, will be equal to this here, right? And this type of strategy, or these type of equilibrium constants, I mean beta 1, beta 2, 3 and beta N, these are known as the overall or the cumulative stability constants, right? So on one side we have the stepwise type of stability constants, and on the other side we have the overall or the cumulative type of stability constants. But we are talking about the same reaction here and two different strategies. We can say here that because the reaction is same here, there must be present some relation in between the K or the stepwise stability constants and the beta here, that is the overall or the cumulative stability constants, right? So we will try to find out that what is the relationship between the K and the beta for an equilibrium type of reaction regarding the thermodynamic stability of the complexes. Okay, now let us start from the expression for the beta 3, which you can see here. The beta 3 is what it is. For one metal, 3 ligands giving Ml3, the beta 3 is what it is, the concentration of the product, I mean Ml3, which you can see here, divided by the concentrations of the reactant, which is a single metal ion. The concentration is represented here. And 3 ligands, which you can see here, the concentration of ligand raised to the power the number of moles, right? So we are taking the help of this beta 3 actually to find out what? To find out the relationship between the K and the betas, right? So starting with the beta 3 here, and let us multiply and divide the numerator and the denominator by Ml and Ml2, right? So you can see here, this is the value for the beta 3 which we have taken from here, and then we are multiplying it and dividing it by what? By this Ml and Ml2, which you can see here. Here is the Ml and Ml2 divided by Ml and Ml2 here, which is this thing here will be equal to this actually, okay, because it will simply cancel out each other, right? So now what we are doing here is that I am just writing this Ml here in the first part, and then is this Ml2 which you can see here, and this Ml3 I am writing here in the last part in this way. And here is what it is my Ml which you can see here, and this is the Ml which you can see here. It is present in the second part of this equation, and here is the Ml2 which is present here, right? And because it is L raised to the power 3 here, so we can open it in this way, means one L here, second L here, and the third L is present here, right? And now if you go back to the previous slide, what you will find is that this expression actually corresponds to what? It corresponds to the stepwise stability constant, which is what? Which is the K1 here, right? And this corresponds to a stepwise stability constant, which is actually corresponds to what? The K2. In the same way, this expression here corresponds to the K3, right? Such that we have a relationship between the beta and the K here, and that says what? That beta 3 is equal to the product of the K1, K2 and K3, right? So we can always write that in general the beta for n type of ligands, it will be equal to what? It will be equal to the product of K1, K2, K3, so on until we have the Kn here, right? So obviously, if we have n number of ligands, one metal ion resulting in the formation of MlN type of complex, the beta n will be equal to what? I mean the overall stability constant for these n ligands. It will be equal to what? It will be equal to the product of the K values, right? And K is what? It is the stepwise stability constant. And if we have n number of ligands, it will go to value n here from 1, 2, 3, such that it will go and reach the value n here, right? So this is the relationship between the stepwise and the overall stability constants. So continuing further, we have that same equation here, and if we take the logarithm of this equation, let us say we are taking the log of beta n and the log of this whole part here, And when I will open this logarithm part, it will be what? It will be log of k1 plus log of k2 plus k3, so on up to we reach the kn here, right? So I can say here that because the k1, k2, k3 and kn, these are what? These are the stepwise type of stability constants. So the logarithm of beta n, which is actually a sum of all these log of k's, it will be what? It will be actually a measure of the stability of that complex, right? So if we have one metal plus n number of ligands and we have some equilibrium reaction resulting in the formation of MLN here, such that we will be having by strategy 1 the K1, K2, K3 up to Kn type of stepwise stability constants, and then we will also be having a strategy 2 here in which we will be having beta 1, beta 2 up to what? Up to beta n type of cumulative or the overall stability constants, right? And the relationship between these betas and these k is what it is, this equation here, such that the log of beta n actually represents the measure of the stability of this complex ion formed from these ions here. And finally, we have some kind of experimental data here. And we are comparing what? We are comparing the thermodynamic stability of the tetramine copper complex and the tetramine cadmium type of complex, right? So using that same equation, that is log of beta, because there are present 4 number of ligands here. So obviously instead of beta n, we will be having log of beta 4. And thus it will be equal to the sum of 4 different types of stepwise stability constants, I mean K1, K2, K3 and K4, and taking their logarithms, right? In the same way, even here in this case, because the number of ligands are 4 actually, so log of beta 4 will be equal to the sum of the logarithms of K1, K2, K3 and K4 for these 4 number of ligands, right? So even you can see here that the values are given here for the logarithms of these K1 up to K4, and finally we are having a value of 13.30 for the logarithm of beta 4 for this type of complex. And in this case, we are having a value of 7.12 for logarithm of beta 4 for this type of cadmium ammonia complex, right? And one thing, if you look carefully on this part as well as on this part here, you will find that as we are going from K1 to K4, the values of these constants is actually decreasing. You can see here it is approximately 4 here, then 3.6, 3.1 and 2.30, right? So we can say here that the K1 is having a higher value as compared to K2, which in turn is having a higher value than K3, and K4 is having the minimum value, right? So let us try to find out that why it is happening in this complex here. And the same situation is present even here in moving from this K1 to this K4. The values are decreasing from 2.56 to 2.10, 1.44 and 0.94, right? So why it is happening? We can say here that if you think about K1, it means what? That it is the equilibrium constant for a single metal ion and a single ligand, right? If we go back to the previous slides, we will see here that the K1 is what actually it is for a single metal and a single ligand, right? And what will be K4 here? Of course, K4 will be equal to Ml3 here plus one ligand giving what? Ml4. This means whatever stepwise stability constant K4 will be there, it will be for the metal ion having 3 ligands with itself plus addition of one ligand giving this type of Ml4 ligand, right? And now let us go back to our present slide, which is this one here. So we were saying here that K1 actually corresponds to a single metal ion and a single ligand, resulting in the formation of a complex something like this, and we are going stepwise here, right? So you can see here we are having a single metal ion, single ligand. Obviously, when the ligand will be approaching this metal ion, the repulsions will be low here, and thus the equilibrium will tend to shift in this direction, giving a larger value of K1, right? On the other hand, if we talk about the K4, this means what? That the metal ion will be having already 3 ligands with itself, and we are left with a single ligand, that is, you can see here one ammonia we are adding here, resulting in the formation of this copper tetramine complex, I mean this one here. So what will happen here is that the single ligand is being added to the metal ion which is already having 3 ligands with itself, and when it will be approaching this metal ion, it will be experiencing a lot of repulsions from these 3 ligands which are already present with the metal ion, right? Such that here in this case, because of these repulsions, the reaction will be in this direction but not at a very high speed, right? So the value of this equilibrium constant, I mean the K4, will be quite low here, right? And this you can see here, the K1 value is quite high and the K4 value is quite low. In the same way, even for the cadmium complex, you can see here the K1 actually corresponds to a single metal ion, a single ligand, resulting in the formation of this complex stepwise. Once again, I am talking. And the equilibrium constant here is the K1. So because the ligand here is approaching a single metal ion and there are no other ligands here which will be causing repulsions, so there will be present less repulsions here, and the equilibrium will tend to shift in this direction at a very high speed, giving what? Giving a high value of this K1 here, which you can see here, it is 2.56, right? On the other hand, if we are talking about the K4 type of stepwise stability constant, this means what? That if we want to prepare our cadmium tetramine complex, we will be adding one ammonia to this part here, which is already having 3 ammonia ligands with itself. So when the ammonia ligand will be approaching here this metal ion, because it is already having 3 ligands, it will be causing a lot of repulsions, and thus in this direction the equilibrium will slow down, giving a low value of the K4 here. The value will be quite low, which you can see here, it is what? It is 0.94, right? So this is the reason why we are having this type of order. I mean this type of order here. Whenever the formation of any complex takes place, it is all happening because the K1 actually corresponds to a single metal and a single ligand. At that point, the repulsions are quite low, so the equilibrium shifts very fast towards the right hand side, forming that complex, giving a very high values of K1. And when the reaction goes towards the end, I mean the formation of the overall complex which contain 4 ligands, the last step is what? It is the reaction of a single ligand with that metal ion which already have 3 ligands with itself, giving a large amount of repulsions. The equilibrium will slow down towards the right hand side, giving small values of later stepwise equilibrium constants, I mean the K4 values, right? So the K1 will always be higher and the K4 will always be lowest, right? Which we are seeing from this even data here, right? And finally, let us talk about the values, I mean the overall values here, which is 13.30 for the log of beta 4 for this copper complex, and 7.12, that is the log of beta 4 for this type of cadmium complex, right? And at this stage, I think there is no need to tell you people that, because it is having a higher value of the overall stability constant, so thus this will be more stable as compared to this complex here, which is having a low value of the stability constant, so it will be less stable, right? So in general, we can say that a complex having a high value of the logarithm of beta, that will be more stable. And moreover, if any complex is there in which the log of beta is more than 8, that will be a stable type of complex, right? So in this case, you can see here this value here is less than 8 here, so it is very, very less stable type of complex, right? So finally, we can say here that the values of the stability constants may be the stepwise or the overall or the cumulative stability constant. It actually indicates the relative concentrations of the species at equilibrium, right? So you can see here this equilibrium reaction. We are having species on the left hand side as well as we have species on the right hand side, and we can see here that this is our complex here, and these are the constituents ions here from which our complex is being formed, right? So whatever values of the K and beta will be there, these will be actually representing the relative concentrations of these ions at equilibrium or these species at equilibrium. A larger value of the stability constant will indicate that the concentration towards the right hand side, I mean the complex, will be greater, as compared to that of the ions from which it is formed, I mean which are present on the left hand side, right? So you can see here the larger values of the stability constant indicates that the concentration of the complex, I mean this thing here will be higher as compared to that of the concentration of the ions from which it is being formed, I mean the M positive and these ligands here, right? So the higher stability constant means the higher thermodynamic stability of that complex, right? So for this equilibrium reaction, if the stability constants are higher in this case, this means this complex will be having high thermodynamic stability, and this equilibrium will be shifting towards this direction or the right hand sides. So this is all about this very first lecture on the thermodynamic as well as the kinetic aspects of the transition metal complexes, in which we have seen that what is meant by a thermodynamic stability of any complex, and moreover we have got some idea that what different kinds of stability constants are there. We have the K stability constant, which is known as the stepwise, and there is also present a beta type of stability constant which is known as the overall or the cumulative type of stability constants, right? So this is all for this lecture here. Thank you so much.